Sure, please go ahead.
Morning all. Morning all. I am Karthik Reddy, a research scholar. Welcome you all for the day 3, session 2 of an NAMPET sponsored short-term online course on power electronics converters applications in microgrid and vehicular technology from 20th July to 24th July 2022. Organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela, Odisha, India. It's an honor and a privilege to read the biodata of Professor Dipankar Debnath. Professor Dipankar Debnath joined Indian Institute of Technology, Kharagpur as an assistant professor in the Electrical Engineering Department in 2016. Prior to joining IIT Kharagpur, he worked as an assistant professor at IIT Indore, research associate at IIT Bombay, both at the Electrical Engineering Department. He was conferred with a PhD degree along with an excellence in PhD thesis work from the Indian Institute of Technology, Bombay in 2015 for studies in power electronics and power systems. He has done his ME from IIEST Shepur, West Bengal, and BE from NIT Agartala, Tripura. His research electronic converter topologies, design of solar photovoltaic based standalone off-grid systems for rural areas, multifunctional inverter for grid integration of renewable energy sources, study of microgrid, motor and motor control design for an electric vehicle, etc. I request Professor Dipankar Debnath to begin the session. Over to you, sir. Thank you.
Thank you for the nice introduction. Am I audible clearly?
Yes, sir, you are clearly
audible,
sir.
Okay. First of all, my sincere apology. I don't have a strong internet connection also. I can manage having a video maybe after 2 minutes to gain. Welcome and thank you for listening to me with the participants. And I also extend my hearty welcome to you who near the area visit IIT Kharagpur. Would love to host you. You can visit our labs, and if our research interest matches, we can also jointly do some research. I think like let me share the screen and start the presentation. Please confirm whether you can see my slides or not.
Sir, it's not yet shared, sir. We are unable to see. We are able to see you, sir, but not able to see your slides.
Yeah. Just give. I'm sharing and please confirm.
Not yet started, sir.
Yeah, I have shared that. Yes. Okay. Delay. It is not yet done?
No, not yet done, sir. Please do it once again, sir. Still, it's not coming, sir.
It is showing messages that micro screen.
Sir, could you please rejoin or I think it might be solved if you rejoin.
Yeah, I'm just trying to say. Just try for the last time, then I'll rejoin.
Okay, sir.
Is it? from?
No, sir, it's not started.
Okay, then yeah.
No, sir, it is not yet visible.
We request the participants to be in online. Professor Dipankar will rejoin and start the session. Please wait.
Yeah, I have joined again and
Yes, sir, it is
I'm
visible now.
sharing the entire screen. Okay.
Yes, sir,
Yeah.
visible.
And I have made it full screen. Please confirm.
Yes, sir, fine now. You can continue now.
Okay. Thank you for your kind patience. And for today's this discussion, I'll be briefly touching upon this topic: motor control unit for electric vehicles, and what kind of protection features we need to embed into them. And also, we'll briefly discuss this topic: fault tolerant operation for electric vehicles. Since it's quite a long talk, I don't want to talk continuously. So I would request the participant to help me. And in between the talk, I'll be asking you a few easy questions, which will be more or less revision type of questions. So please unmute your mic and respond as much as possible to make this session more interactive, right? And we should enjoy the session as much as possible. So I would expect your kind cooperation throughout this session. And I'll try to wind up by 1 o'clock. And then dedicate 15 minutes discussion session. Also, in between, if you have any doubt, please unmute and let me know if you have any queries. Further, I'll be sharing the slides with the organizing team and they can share it with you. So you need not note down anything, only maybe the important points, right? So slides will be available to you. Now, before going to the main technical part, let me quickly touch upon what topics right now me and my teams are working on, so that you can get a glimpse of the activities that we are doing at IIT Kharagpur in my team. Of course, IIT Kharagpur has a very strong team in power electronics and motor drives area, and I am just one of those faculties, and I am representing the part that I have been involved with. Right, it does not represent entire work being done at IIT Kharagpur. So one of our recent work was we developed a PLDC motor, a smart motor controller, along with a more informative display for electric three-wheelers, which may see on this. I believe my cursor is visible. Let me check again. Yeah, this kind of electric rickshaw was the target, and we have such that it is down, especially control for other light duty electric vehicles. And a detailed demo of this video, like what are the advantage our solution as compared to off-the-shelf solution available in market, you can watch this video. I'll be sharing you the link. And this, based on this work, we have already done a technology transfer. So this development now will be into production. Hopefully, in next 2-3 months at least, you will be seeing the BLDC motor coming up in the market. And this work was covered by several Times of India, Economic Times, and so on. Next, what we are involved with basically doing different kind of motor design. One is synchronous reluctance motor. This motor can work without using any permanent magnet. And in case you want to improve the performance, you can provide some assistance through some permanent magnet, which need not be rare earth permanent magnet. For example, you can add ferrite, and you can improve the performance of this kind of motor. Main motivation here is that you can reduce spend the rare earth permanent, which is available in chat. And comparatively, ferrite is a magnet which is also available in India, and of course at much cheaper rate. On similar line, we have also worked on switched reluctance motor, which is again based on a non-magnet kind of design, and it's a very special kind of motor which needs a special kind of power converter also. So it is not like a regular DC to AC converter that we use, and I repeat, they need a special kind of converter. We are also working on permanent magnet synchronous motor drives for electric vehicle. A small team is working on the battery charger side, mostly on the domestic charger level, less than 3.3 kilowatt. Also, one of my team is dedicatedly work on solar photovoltaic systems for rural application mainly, but those can be modified to grid connected or both hybrid, off grid as well as grid connected system. Our schemes are capable of catering DC load as well as AC load together. And in DC load, we can offer 48 volt. We can also offer higher voltage like 380 or 400. And AC load, typically we have targeted the domestic single phase appliances. So main target or philosophy here is that how you can provide several features without using many number of semiconductor devices. So basically how you can design an integrated power electronic converter solution which can do job of 2 or more converters, so that you can come up with a compact solution without using many number of semiconductor devices. So generally that leads to higher efficient system, less size component solution, etc. Now coming to today's discussion, mainly we'll be focusing on the motor control unit, right? And you will understand later on that the concept that we'll be discussing, they are equally or at least similar in application to other type of converter which are used, for example the battery charger, the DC-DC converter that are required for catering auxiliary loads, right? So we'll be focusing mostly on motor controller unit, but you can extend them to other power electronic converter also. And some of the protection feature we'll try to cover in more detail. This topic itself is a big, has a wide content and can itself has a own short-term courses. But what I am trying to give you is kind of a brief overview of the system, while giving slightly more details about 1 and 2, so that if you are interested, you can go deeper into them and you can do your own research as well. Same will go with the fault tolerant inverter topic. What does it mean and what facility you need to provide in your converter, that we'll briefly touch upon. And I'll be also sharing you some reference material. So if you're interested, you can go through more details and maybe we can discuss offline later on if you're interested. I hope you will remain charged throughout the session and you will enjoy this journey. Please try to be as much interactive as possible so that both of us we can enjoy this journey. So on this same front, I would like to hear from you. This electric vehicle, as you can see, it is quite is gaining a lot of interest, and the motor is one of the most important part of an electric vehicle, right? So what do you think, which motor are most commonly used for electric vehicles, specifically for four-wheeler category? Can you help me with the answers? Which
BLDC
motor
motors.
is, yes? Can you repeat again?
Sir, BLDC motors.
BLDC motor. Okay, so one answer we have got BLDC motor. Any other answer, please?
PMSM.
Okay, so we have got answer BLDC, PMSM. Any other answer?
Induction.
PMDC motors also.
Permanent
PMDC.
magnet DC motor. Okay.
Induction motor.
Induction motor, right? Any other motor can you think of?
SRM maybe.
Yeah, SRM is yet to, as per my commercial study, they are yet to be used in commercial vehicles. But I have not come across any commercial vehicle. Maybe that may be a solution. But main problem with SRM is that they have high torque ripple and they have comparatively bigger size, less power density. So they are not the present choice, but maybe in future we'll see some of them.
The DC
So yeah, someone said DC series motor, is it?
Not series, DC motor, just means separately excited or permanent magnet DC motor.
Okay, let me increase my volume. It looks like I'm not listening to all the statements. Yes, can you repeat the argument?
Sir, permanent magnet DC motor means the DC motor with permanent magnets.
Okay, okay. So let me first tell you, let me take it to the market survey of what exactly commercial four-wheeler are used. Right? So Toyota bias, which is one of the not they were popular at the initial levels. Toyota is permanent should see permanent magnet synchronous. And then if you look at Honda, Chevrolet, Ford, them are using permanent synchronous. Please confirm whether you are seeing my cursor or not.
Yes, sir, we are able to see.
Thank you. So if you see that, if you observe in this slide, all four there magnet synchronous motor. Does not mean that all electric vehicles are using permanent magnet synchronous motor. We'll see some other. Now, if you look at some of the older version of Tata's electric vehicle kit, they were using induction motors, right? Okay. So here goes another question for all of you. What do you think? Which electric vehicle is the most selling now in India? Which version or other? What is the name of the vehicle? Tata Nexon. Thank you for being such a nice audience. And any idea which motor they are using?
PMSM.
It is PMS, right? And follow Tesla other version, they were actually using induction motor. But now Tesla's recent model, they are using kind of a permanent magnet assisted synchronous reluctance motor. So they're also shifting towards permanent magnet based solutions. So if you summarize this, you will see that the first choice for electric four-wheeler. So let us categorize it. For electric four-wheeler, the first preference is PMSM. Second preference seems to be induction motor. Okay, and these two are mostly used. SRM is not used, as I told you. What is the reason? A permanent magnet-based DC motor is also not used because there are so many drawbacks, including those required for brushes and magnets. Even if you put permanent magnet the field, still in the armature you have to do those armature coils, right? And you have to do those commutator brush arrangements. So those are not very suitable for a electric vehicle applications. You know, there are some sparking to power density issues, etc. And they are not for depression also. And coming to BLDC, BLDC is a very special motor which is generally preferred when your power rating requirement is around typically less than 5 kilowatt. So you will see BLDC is the #1 choice for electric three-wheelers. Electric three-wheelers require motor rating of around 850 watt to 1000 watt. Okay, so roughly 1 kilowatt you can assume. And in this range, the electric three-wheeler, the two-wheelers, they are mostly using BLDC motor. But again, if you see some high-performance two-wheelers, like maybe some of the Ather's model or Ola's model, which offer higher speed comparatively and high power rating, they are actually famous, not BLDC. But if you look into the some model by Okinawa or Oriva, those kind of scooters, not bike, they are mostly based on, right? So let us quickly summarize and help me again. For four-wheeler, what do you think? Which is the most commonly used motor now? PMSM, right?
PMSM and induction motor.
Yes. PMSM is the #1 choice, followed by induction motor, right? If you do the commercial market available solution study. Then for slightly higher rating vehicles like bus, truck, train, there also you will see induction motor and PMSM being the most favorite choice. For electric three-wheeler, as I told you just now, mostly they use BLDC, right? For two-wheeler, if power rating requirement is typically less than 5 kilowatt, generally people use BLDC. More than 5 kilowatt, they go with the PMSM. And typically, if the rating is less than 1 kilowatt, right, then most of the choice will be using hub motor, where you are mounting motor directly on the wheel, right? So those hub motor, which are basically outer rotor configuration, they are used typically when your power rating requirement is less than 1 kilowatt. And beyond that, you still use BLDC till 5 kilowatt, but those will be mounted somewhere in the mid section of your electric two-wheeler, right? They are not mounted on the wheel, and then they will be connected through the wheel by chain belt element. And so you can see most of this present market are flooded with BLDC and PMSM, right? But problem with BLDC and PMSM is that they use rare earth permanent magnet. Now, example of rare earth permanent magnet are anti-FeB and samarium cobalt. And these are mostly China, around 90%. And some percentage are available in Brazil. So now you can understand the several political, economical problems with our availability of magnet within India, right? And this problem is there for several other countries also. So nowadays, a lot of research is going on how you can design motor without using rare earth magnet or using less amount of rare earth magnet, right? So that you need not depend on foreign import. So now this synchronous reluctance motor and switched reluctance motor, a lot of attentions are being given towards them. And if you look at the motor control structure, right? Finally, in electric vehicle you will be having battery, which will give you DC power supply. Now, for most of the motors that are being used in electric vehicle, you will see this kind of DC to AC converter. So input side is your battery, giving you the DC. Output side, you need mostly three-phase AC power supply. So be it PMSM, BLDC, induction motor, synchronous reluctance motor, they require three-phase AC power supply. But SRM, switched reluctance motor, is a special category motor which does not need AC power supply across a terminal, and it needs only unidirectional currents, right? So the power converter required for SRM is a special kind of power converter, which is not similar to other motors, right? Please keep that in your mind. But mostly, as I said, this kind of converter, which is known as voltage source, is preferred and used in several electric vehicles. We'll focus mostly on this VSI, voltage source inverter, and we'll try to see what kind of protection we need to provide so solution is more reliable and they can last. Participants, I request you to kindly mute your mic If you have any question, then you unmute so that we can get to know. Thank you for your. Now, this part is basically for someone who is not very conversant with the practical converter, right? See, when we study power electronics as a theory, generally we study books like Ned Mohan or from Rashid or sometimes P.S. Vimra, Ericsson, etc. So there, mostly you will see when someone is discussing DC to AC converter, you will see this kind of images similar to this. So you will have a feel like you need only 6 semiconductor devices, maybe MOSFET, IGBT, etc. And sometimes a capacitor at the input side. And it looks like inverter is done, right? A DC to AC converter is done. But once you want to implement a DC to AC converter, basically now we are referring it as a motor controller for electric vehicle. You will see, in addition to this component, you need some other component also, right? For example, for doing the speed control, etc., you need a digital controller nowadays, right? Mostly. So you'll be using a microprocessor or a digital signal processor, those kind of solutions. So this is what I'm referring here by this term controller. Now this controller will take information from the. Hello. Any question? Yeah, I think one of the participant has unmuted the mic by mistake. Dear organizing team, if possible, please mute the other participants. So basically, the driver will give you the command through accelerator, through the brake command, through forward reverse direction command. Those will be mostly mechanical command, and they will be sent to your controller after converting them into suitable electrical commands, right? Because the microprocessor will understand only information sent in terms of voltage. So you have to convert all those non-electrical quantities, and then you have to send to the microcontroller. Same thing goes with the motor. So if you want to measure the speed of the motor, you will be using a speed sensor or position sensor. Then finally, you will be sending a equivalent voltage command to your controller. So those conversion, some non-electrical quantity to suitable electrical quantity, those things will be done by a suitable sensor along with the signal conditioning board. Then based on the logic of your algorithm, it can be field oriented control, it can be VYF control or director control, etc. Your controller will generate suitable gate pulses for these semiconductor devices. Now microcontroller cannot drive the semiconductor devices directly. It will tell you when to turn on and off, and based on that you will be using some sort of amplifying circuits, and sometimes you will need isolation also. Those things will be provided by the driver circuit, and then finally the gate pulses will be given to your semiconductor devices. So in a nutshell, it is not only the 6 semiconductor devices, you need so many other components to practically build a converter in your lab and finally to make it to the product level. Now, when you make something at the lab, you have luxury, right? You can make it wide open. You can, you are not very bothered about the size, etc. So you generally design something like which is shown in this image, which we call it laboratory prototype, right? So in this image, you can see the heat sink for dissipating the heats. Then you have to mount everything in a PCB. This part is kind of the driver circuit I was referring to. Then this green board was the sensing interface board, etc. But once you want to put them into a product, right? You don't have luxury to make them in such a open kind of fashion. Finally, everything has to go into a close enclosure, right? And so many other design consideration has to be put in to make a final product. Now, this one, as you can see on the right side top, this is basically a motor controller unit, which is presently used in electric three-wheelers. So you can see how a practical product looks like. And if you open it up to see how the components, etc., Hello, am I audible?
Yes, sir, you are audible, sir.
Okay. It looks like I lost connection for a few seconds. Can you see my slides? Can you please confirm?
Yes, sir. Your slides are visible, sir.
Okay, thank you. So what I was referring to is that if you open any practical motor controller unit, you will see that they will be using several components, right, which are not shown directly in the circuit diagram. One more interesting observation you will see that they are using so many different capacitors. Even though in my diagram I showed you only one capacitor, practically you will see they are using several capacitors, right? And then there will be some auxiliary DC-DC converter, etc. And this one you are seeing in your screen is basically a motor controller unit taken from a four-wheeler. Now I cannot disclose the vehicle name due to some NDA agreement. So, but you can here also you can see that these are based on IGBT. This is for high power rating, and what you are seeing on the right side, this is basically one leg. So two IGBT connected in series, and you can see on the left side image also. See here they are using so many capacitor, right? Now in the circuit diagram I showed you only one capacitor, so we'll discuss this why in practical situations they need so many capacitor, and what about the other component, etc. slowly. Again I'm showing you another motor control unit taken from a four-wheeler, but it is of slightly lesser rating. So the motivation behind showing you all this is you can see how practical motor controller which are commercially available, how do they look like, so that if you're targeting finally in any product development, um, you must have a target. So you must have end finishing like this. So with this, I have again come to a revision or kind of a quiz slide. Uh, this we have already discussed. Most popular motor for electric vehicle we discussed, it was PMSM. Now can you help me with the second question? Most commonly used motor controller topology. The DC to AC converter we use, is it a current source inverter? Is it a Z source inverter, or it is a voltage source inverter? Which one is the most commonly used solution? Can you help me quickly?
Voltage source inverter.
Voltage source inverter, right? Thank you. Can you help me with this third question? Which motor requires a kind of a different power converter, which is not similar to the other motor requirement?
SRM.
Which motor? Yes. Can you repeat your answer, please?
SRM, sir.
SRM. Yes. Thank you. And any idea for except SRM, if you talk about mostly the PMSM and induction motor, what kind of speed control strategy they use? Is it VYF? Is it FOC? Yes.
FOC.
FOC. Yes. It looks like the best choice. I'll skip some of them. So in the next slide also, I have kept few questions for your revisions. Today, due to shortage of time, I am not going into all of them. Please see, check them in your free times. Okay. And if you have any doubt, let me know over email. Right now, time is almost 12. So I'll continue for another 15 minutes and then we'll take a short break. And I'll try to show you a demonstration video of one of our products. Right. Now, one of the very important question that why we actually need this capacitor at the input side. And believe me, it is one of the very popular Viva questions, at different interview boards, be it MTech or PhD selection, or sometime an industry job also. So the question goes like something in this form. In this diagram, you can see a capacitor which is connected directly in parallel to the battery, right? Take it as an electric vehicle example. Now, as we know, the current in a capacitor is given by C dV dt. And we know that battery voltage is more or less steep. So then this dV dt looks like it is going to be zero, right? Because change of voltage with respect to time is almost zero. It's a battery, right? So then current flowing through the capacitor is also zero. Then question is, why do you need this capacitor? So this is the question. If you would like to attempt to solve this question, you are welcome, right? I hope you have understood the question. Why you need this capacitor when it looks like it current is going to be zero? Anyone would like to answer this question quickly? If you want, I can repeat the questions.
The current is ripple free.
It looks like it is zero. So zero means it doesn't have any value, right? A similar question can be asked for op-amp. So those who have studied op-amp, you know op-amp has a infinite input impedance, right? So if you remember, we used to draw op-amp like this. There will be a plus and minus terminal, and we know ideal op-amp is having infinite input impedance, right? And then you may have some feedback resistance. Here it goes your input. Here goes your another input, and maybe ground is connected here to another resistance or capacitor. So question is if yes, please.
Battery is ideal battery, sir. No internal resistance and all.
That you have to figure out. See, this is for a practical situation, right? Practical converter. Can a battery be really ideal?
No. Okay.
Definitely no, right?
Yes.
So if it is having an internal resistance, why you need capacitor still? I think actually it needs some time to go into this type of analysis, and I am sure most of you know it, but maybe you're hesitant to share the answer. Now, for the sake of time, let me give you two reasons, and you think more about it, right? And then later on, if required, we'll discuss. One of the practical reason why we need this capacitor is, see, in this diagram, everything looks ideal, but as you rightly pointed out, batteries are not ideal. So definitely there will be some internal resistance and sometimes little bit of inductance, right? And parasitic capacitor, those elements. Now, due to them, this dVdt is not going to be zero. So definitely capacitor current is not going to be zero if you consider practical scenario. Okay. So now you can always ask, so what if? What will happen if I don't use the capacitor? Is it mandatory? So I will say, as a practical experienced person, that this capacitor is absolutely mandatory. Without it, you should not design almost any power electronic converter. So main practical reason is, see, when you are designing a power converter, finally you will be mounting all your components in a PCB, right? Now, there are several sources of getting some parasitic inductance. So, by the term parasitic, I am referring to those inductance which are not added deliberately. These came due to your flaws in your PCB design, or sometimes you have a long cable connecting your battery to the motor control unit. So, that long wire will have some inductance. Inside battery packaging also, you may end up with some inductance, right? Now, let us see, if you don't use capacitor, what is the problem? So just focus on this solution. Let's say you have a battery right here, and then a very small unwanted inductance of, let's say, 10 nanohenry, right? These are just for number, right? For you to understand. Now, let's say this capacitor was not here. Now, when I turned on the top switch, or rather one of the switch, let's say current flowing was 100 ampere, just to give you an example, right? Now, next time when I'm turning off the switch, if there is no capacitor here, there is no current path for that parasitic inductor to flow, right? Now, all of us know, being an electrical engineer, an inductive circuit should not be broken. Otherwise, it will lead to a large LDIDT, right? Basically, it will lead to a large voltage appearing across the inductor. Now, where this voltage is going to appear, or what it will lead to. See, if you follow a simple KVL, there is a battery voltage source, large voltage appearing across inductor, the switch was open, so most of the voltage now will appear across the switch and your switch will get damaged, right? So this is basically consequences of breaking a circuit. We shall. So basically, what you're doing in your inverter, you're doing high frequency feedback. You are turning off your switches at seconds. Isn't DT time? The switch actually takes to turn off maybe 1 or 2 nanoseconds. So this DT is very, very small. And what about DI? It can be very large, because when switch is off, your final current is going to be 0. And when switch was on, the current I1, it could have, sometimes it can be 100, sometimes it can be more also, less also, right? So now if you do some mathematics, you will figure out sometimes this inductor voltage can be much higher. So this parasitic inductance is basically creating a high voltage across it, and that may appear across the switches, and that can simply burn your switches. Now, solution to this is that we must use a capacitor very physically very close to the switching devices. This is very important. When drawing circuit diagram, I'm not highlighting that point, but practically, when you will be connecting a capacitor, at least 1 or 2 capacitors must be very, very close to the switching nodes where your physical switches are present. So even though there are some inductor present in your design or in your input side, they will get a path through this added capacitor now. And as a result, you are not going to experience that large LDIDT or large voltage across inductor, because it is already getting a path. That's how your switching devices are going to get protected. Now, sometime in your design, you may have one switching leg at one place, another switching leg may be slightly, let's say, 10 centimeter away or 5 centimeter away. So most of the time, what we do, we try to put a capacitor across the bus to your switch leg location, so that even if you have some parasitic inductor forming here, it will still get a path through this added capacitor. So this is basically to protect your switching devices from parasitic inductor and its unwanted effects. So this is one reason. Second reason is that since you are doing a lot of switching in your inverter, your DC input current is not going to be a flat DC or form. It is going to be a this inverter input current finally it is converted by battery, right? If you do not use any capacitor, ideally you want battery to with a renewable, right? Because that is actually contributing to this is the word will be which is responsible for power delivery. You some which is some average component and with some superimposed AC component, which is basically the ripple part. This ripple is not contributing to your power delivery. This it is extra cost battery. Battery is the internal distance. So if dump more and if you have more current resistance, it will get more heat. Ideally, you are supposed to draw only average component of current, but now you're drawing average plus some superimposed ripple current. Now those ripple current, they are not actually contributing to power delivery, but at the same time, they are adding up losses. And as you know, more losses means more heat development. And more heat development will get degraded, right? So ideally, we should have a solution that battery supplies only the DC component of current, the average component, and that ripple component should come from the capacitor, right, or some other element. So capacitor is the best solution. That's why your actual inverter input current will have average as well as AC component, which is the ripple component. Average component will come from the battery, and you must be designing your capacitor such that it provides you that unwanted ripple part, which anyhow has to input current. So these are the two major reasons that capacitors are absolutely mandated in this kind of motor controller design, or mostly any power electronics design. Now, in the next slide, I'm going to show you even an interesting figure. Practically, when you use this capacitor, see, this is finally going to your inverter. So this right side is actually going to your inverter input, and your battery is actually at the input on the left hand side. So in the left hand side, you're battery, and in between there is several capacitors, right? Now, very interestingly, let us try to discuss, and then if you have any question, I'll take up, right? And then we'll take a short break also. So first question you can see here, interesting observations. Please pay your attention. Here, we are using two numbers of 220 microfarad, okay? And you can see plus mark and the top side plate, right? But for the other capacitor, you see there is no plus marking. And also these are kind of flat lines. If you look at this one, you see there is no plus marking. The capacitor has flat line. But if you look at the other two capacitors here, they have plus marking. At the same time, the bottom plate is kind of carved. Okay. So those who knows basic capacitor symbol, you will understand these two capacitor in the box. These are basically electrolytic capacitors, right? Now, this electrolytic capacitor will be mainly responsible for the filtering and those energy storage, ripple elimination part. And other capacitors, they are mainly responsible for those LDI, DT, and high frequency ripple elimination. I'll go one by one, and then I'll take up your questions. Right? Just give me 2-3 minutes, and then I'll take up your questions. Let me finish this part, and then I'll take up your questions. Hello. It looks like someone is speaking. I'm very sorry. I'm not getting your voice clearly. Can you speak a bit louder, please? Or anyone from the organizing team, can you help me understand his question in case it is having? Or let me just finish this part, then I'll be open to your questions. So what I'm telling here is that first focus on this electrolytic capacitor, and you can see we are connecting two number of capacitor. In practice, there may be several capacitor connected in parallel. Why? You know, these capacitors, mostly they'll be electrolytic capacitor, like as you can see in this right side diagram. They have limited ripple current handling capacity. Okay, so you see, on one of the reason I told you, this capacitor, one of the main requirements is that it is to provide you those ripple current, so that battery can give you ideal DC component. Now, this ripple current, any practical capacitor have its own rating, and higher the ripple current requirement, you have to use a electrolytic capacitor with higher ratings, right? Now, unfortunately, electrolytic capacitors are not available with very high current rating. So practically, you have to connect them in parallel to increase their ripple current rating. And it will also help you to reduce the ESR value, which is equivalent series resistance. Okay, a practical capacitor will have some equivalent series resistor and it will have some losses, right? So if you connect more capacitor in parallel, their current rating will increase. At the same time, their ESR value will come down. So efficiency will improve. Okay, this is electrolytic capacitor. Now, interestingly, you see, even though you're using large value, see 220 microfarad connected in parallel, you 440 microfarad. Now, even though you are using such a high capacitance, you see here you are using just a 10 microfarad capacitor, that too, two of them in series. So equivalently, it is only 5 microfarad. So you have connected 5 microfarad in parallel to 440 microfarad. Now, why is that? And the answer lies that these two capacitors are actually different. One is electrolytic, another will be maybe a polypropylene or ceramic, those kind of capacitor. Why? Because electrolytic capacitor will offer high impedance at high frequency. Okay. So now what you do, you open a data sheet of a practical capacitor. Let's say you take an electrolytic capacitor of this rating and try to see their data sheet. You will see a frequency response, which generally we don't discuss in our regular classes. So as your frequency increases, how the impedance offered by the capacitor varies. So ideally, we assume that capacitance value will remain same and impedance offered by the capacitor will remain same irrespective of frequency. But this is a wrong statement when you think practical capacitors. Okay. So for high frequencies, you will see most of the electrolytic capacitor will offer higher impedance. So then they are not a good filtering element at high frequencies. That's why we should select a capacitor to give us high filtering action for high frequency component. That's why you see these small value capacitors are used basically to support you during high frequency operation. Now you know what is going to be your switching frequency and what is going to be your switching ripples, so you can design this capacitor accordingly. Next question you can ask that why two capacitors we need to connect in series, right? I could have connected a single capacitor because if I connect two capacitors in series, their value is going down. Why should I connect two of them in series? Practical reason is that these small tiny capacitors, these are not mechanically very strong capacitor. They have a very weak lead, right? You must have seen some capacitor, right, in your lab, those yellow colored capacitor or little box type capacitor, which are very small in size. Now, when you put them in a PCB, an interesting phenomenon occurs. When you are designing a high power rating PCB, right? Let's say 10 kilowatt, 15 kilowatt, 30 kilowatt. When there is you are operating at those high power rating, there will be heat generated into your PCB, in your heat sink also, right? And then due to those heat generation, there is a chance of expansion of your PCB. There may be some bending of the PCB also, because you are dealing with quite high amount of heat. Finally, through the heat sink and cooling arrangement, those heat will be taken out. But some part of your PCB still may get exposed to those higher heat development. Now, as a result, what may happen? Your PCB may experience a condition known as flexion. Okay, FLEXION. Or you can see contraction or expansion of the PCB due to heat development inside your PCB when you are operating at different power conditions. Now, if you put a single capacitor here, and due to those expansion or let's say contraction, if the one capacitor gets short circuited, then your entire DC bus will get short circuited, right? So you should not allow that situation. Your battery will get short circuited. So what we do, we connect two capacitor in series. So even though one of the capacitor is short circuited, other should not get damaged, right? And to ensure it further, what we do practically, you look at here in this side. See, one capacitor, when we are placing them in PCB, whatever orientation we are putting in, the other capacitor we put in at 90-degree orientation. Why? So if contraction comes or expansion comes in one direction of the PCB, one capacitor may get shorted, but the other capacitor won't get affected, right? That is the reason you put physically two capacitor at 90-degree, right? So that you can avoid short circuit in your DC bus. Now, this is a problem with short circuiting of the capacitor. Same problem may come if there is an open circuit in the capacitor, right? So then your DC bus will get open circuited, not DC bus, right? This equivalent capacitor will get open circuited. So to prevent that scenario, we connect two strings in parallel, right? You can see here. So even if one of the capacitor is open circuited, the other string or the other leg still will be in operation, right? So this is the detailed story I try to give you maybe in shortly. I'm not very sure how much you have got, but if you have any question, I'll be happy to answer. And also we can in between we'll take a 5 minutes break. So I repeat, we are taking a 5 minutes break now. I'll be happy to address your queries. And others, if you don't have any query, maybe you can take a 5 minutes break. Yeah, if you have any question, please feel free to ask.
Sir,
I'll be happy
this
to answer. Yes.
yeah, this is Shashank. Sir, we are using only one capacitor in our converter design. We don't know the actual situation. I mean, what is happening with the PCB? Now you are cleared that doubt, sir. That
Right.
it is
Yes, please go ahead.
the PCB is expanding. We are using only one capacitor in our converter design.
Yeah.
And now we get the solution.
Actually. If you open any commercial product, right, maybe a simple DC power supply, you will see that they are using a different type of capacitor in parallel of different values. I think now you will be able to relate why they use those. And this itself is a good interview question. Okay. Anyone else with any other question on this?
I
Or
think
if
there
you
are
have
no
any...
more questions, sir.
Okay. Okay. Can you please check in the chat box if there is any question?
No, sir, there is no questions right now.
Okay. So then what I'll do, we'll be taking a 2-3 minutes break. In the meantime, let me play a short video for all of you. Of course,
Sure, sir.
watching is not mandatory. Just confirm whether you can hear the audio or not when I play the video.
Sure, sir, sure.
To make it suitable for other application like two-wheeler and heavy-duty three-wheelers, etc.
Audio is
Are you
audible, sir.
hearing the...
Yes,
Okay,
sir.
okay.
Audio is audible.
Okay, so I'll play the video for approximately 4 to 5 minutes so that you guys can take a break also if required, and I'm also getting a break. Please
Sure, sir.
watch the video. Now let us see a demonstration of this product in a running electric three-wheeler.
Hello, I am Yashdeep Shrivastava, Project Assistant at IIT Kharagpur. I am going to demonstrate the integrated motor control and vehicle control unit developed at IIT Kharagpur in association with industry partner Brushless Motors India. To complete the package, we have also developed a 1.5 kilowatt BLDC motor for the same application. For the demonstration, we will be mounting the prototypes of the developed motor and the controller unit on a commercial e-rickshaw. The 1.5 kilowatt motor has been coupled with the gearbox of the e-rickshaw, which transmits the power delivered by the motor to the wheels through an open differentiator. The power and hall sensor connections of the motor are routed through the wiring harness to the controller bay below the driver's seat. In the controller bay, we have the integrated motor control and vehicle control unit, which receives the driver inputs such as the acceleration and brake signals and accordingly controls the electrical power sent to the motor. Now talking about the sensor interfaces, we have the throttle handle to generate acceleration signals, a switch to command forward and reverse direction operation. Similarly, a brake pedal indicates the amount of braking torque required, which allows the controller to implement the brake blending strategy by controlling the extent of regenerative braking. Along with these inputs, the controller also performs the thermal monitoring of all electrical subsystems such as the battery, motor, and inverter with the help of the temperature and current sensor. The controller casing has been specifically designed keeping in mind the vibrational and thermal aspects of the considering Indian roads. Now, a driver will operate the vehicle with 4 passengers sitting at the back. We'll demonstrate the forward and reverse motion and also the performance on a straight road as well as on a inclined road with 4 degrees gradient.
This technology is demonstrated in the required work environment with more than 80% of features verified in an actual e-rickshaw, and so it is TRL level 7 as per Indian TRL definition.
Presently, there is a huge national and global demand for electric three-wheelers, which is around 10 lakhs per year.
Our cost-effective solution will have tremendous impact on savings by avoiding foreign purchase impacting Indian economy.
Coming to the social impact, it will lead to enormous job creation as this subsystem will be designed and developed indigenously. It will lead to less dependency on foreign product. On the safety front, based on present temperature of key elements, the torque will be derated if required, thereby enhancing component lifetime, and Indian certification will ensure additional safety for components, which means safety of driver and passenger will also enhance. The energy optimized control along with the regenerative braking will improve the E-range. Also, better drive experience is ensured through jerk control, better display showing reliable information like fault status, remaining E-range, which will reduce range anxiety. Thank you for watching this video. For further queries, please feel free to write to us using these email IDs. Hello, am I audible?
Yes, sir. Yes, you're audible.
Okay, thank you for watching the video. So this was basically the product that we developed for electric three-wheelers, a BLDC motor and a smart motor controller, and it has several added features. The motor was ICAT certified for IP67. Now, what is IP67? I'll talk in my future slides. A very important concept for protection from outside world, water and dust. Then it was certified for AIS Automotive Standard 041 by ICAT. The motor controller has several interesting features which is not being offered in present electric rickshaws, like remaining E-range. Then we are showing that if some part of the controller is getting faulty, just for an example, let's say your battery voltage is is exceeding the allowable limit or lower than the allowable limit, or let's say your hall sensor is disconnected, throttle is disconnected. So there are several faults which may happen, and if you don't know, being a driver, you are not a technician, of course, you are not an electrical engineer, so you may not know where that fault has happened. Then every time you have to go to a technician, and that technician also may not be very familiar with this content. So what we are basically giving is that if some fault has occurred, we have list of around 25 faults. We are going to display an error code so that quickly you will be able to look at where exactly that fault has occurred, and you can do some rework there to make it operational again. So what we envisage is that it will make the life of driver easier. It will make the life of technician even easier, because he or she need not go and test each and every component, right? Most we are going to give almost the exact location where that fault has occurred. So quickly replace that part or do some connection check, etc., and it should be working again. Similarly, there are two, three other features, and presently we have an industry partner, Brushless Motors India Private Limited. They will be taking up this, and they will be manufacturing them, and hopefully this will see the commercial production soon. And if you know any electric three rickshaw manufacturer or the equipment manufacturer, like motor manufacturer, motor controller manufacturer, who are looking for completely Indian design, we can give them every design from scratch, right? And we can hand over the license, etc. So in case you know someone which might be interested in this kind of product, we'll be happy to help them. With this, let me go to the other part. and we have half an hour left. So I'll try to complete as much as possible, and then I'll share you the slides. If you have any doubt, you can write to me later also. So in one part, I have discussed you this requirement of input DC capacitor and what are the different types required that roughly we discussed. Of course, you can study more about them in some other study materials. Another very important protection, which we have also provided in our motor controller, is reverse polarity protection. Now, if you look at this VSI structure, you can see you are supposed to connect battery only in a particular direction. So positive terminal of the battery, you are supposed to connect to positive bus of your inverter, and negative side of battery should be connected to the negative side of the inverter. Now, by mistake, if someone connects the battery in the reverse direction, so he or she connecting battery positive side to the negative bus of the inverter. If such condition arises, what will happen? Through this body diode of the semiconductor switching devices, you will see this battery is getting short circuited, right? Because diode will turn on as soon as their anode at its higher potential than the cathode by threshold voltage. So this battery connected in reverse direction will create huge current, and it will simply destroy your switching devices. It can destroy your battery also. Now then, how do you prevent from this accidental battery reverse polarity connection? So one of the very simple solution is that you connect a diode in series, right? So even if you connect battery in reverse direction, it won't allow, right? It won't allow current in the reverse direction. That means your switching devices are protected. But there is some problem I'll discuss. Another problem may be using this kind of solution. So here you can see when you are applying uh, battery in the correct polarity, this diode, it can be a Zener, it can be a TVS, it is not going to operate. But as soon as you connect a battery in the reverse direction, through this diode, high current will flow, and then this fuse will get burned. So basically, you are not damaging your inverter switches. Then you replace the fuse and then solve the problem. But problem with this kind of solution is that practical power diode, you cannot use a signal level diode having on-time voltage of 0.6, 0.7 like that. Here you must use a power diode, right? And their voltage drop will be of the order of maybe 1.2, 1.5, something like that. And current can be much pretty high, 100, 150 ampere like that when you are operating in rated condition. In typical electric vehicles, it can be less also. I'm just giving you an answer example. Now, the voltage drop in the diode and multiplied by the current flowing through it, there may be high losses in the diode. Another problem is it don't support regenerative braking. Since the battery current cannot be reversed due to the presence of this diode, you won't be able to achieve regenerative braking, which is one of the biggest advantage of electric vehicle or IC engine based vehicles. So these are some major problems. Another very important term is known as resettable solution. Now, what is it? Let's say a fault has occurred. Now, when you clear the fault, whether the system can operate automatically. If yes, it is resettable solution. If no, it is not a resettable solution. Just an example, look at the solution given in the bottom part. When a fault has occurred, basically your fuse will get burned. Now, if you correct the fault, you correct the battery again in correct polarity, the motor controller is not going to get started because fuse has already burned, right? So someone has to manually replace the fuse, then only the system will start again. So it is not a resettable solution. Whereas the top solution is resettable in the sense when you connect in the reverse polarity, it won't work. But as soon as you connect it in the correct polarity, it will start working again. So you want your solution to be resettable. You want your solution to be efficient, should not have much loss. You also want the system to be compatible with regenerative braking, right? These are very three important criteria of selecting this reverse polarity protection. So one of the solution can be something like this solution you can see in the diagram. So basically what will happen is that this initially the switch S is going to be open. The S switch you are seeing at the top, it is going to be open. So then through this diode and resistor, this capacitor will get charged, okay, for the very first time. Now, if you see that this capacitor voltage has charged to near about the battery voltage, say 90% of it, then you close the switch S. So now battery current will actually flow through the switch S. So then losses in the diode are neglected or almost eliminated. It is compatible with regenerative braking also, right? So this is one of the solution. And in case you connect battery in reverse direction, this capacitor is not going to be charged because through diode you cannot have a negative current, right? So capacitor is not going to be charged, then you are not going to turn on the switch S also. But this kind of solution I have discussed, when you connect the battery in the reverse polarity, motor controller is not going to work. So can you suggest a solution that irrespective of whether you have connected battery in the positive polarity or in the negative polarity, it should work, right? So then your life is much easier. One of the solution is this one. So if you connect battery in correct polarity, shown in the green color, it is basically a single phase rectifier circuit. So input side can be positive as well as negative. Output side is going to be always positive, right? And then you connect motor controller unit at the output. So this will help you to run the motor irrespective of your battery connection, whether it is positive or negative. But again, problem with this solution is that you will have higher losses because now two diodes will conduct at any point of time. At the same time, regenerative braking is not possible, right? So this is not a good solution. Most of the practical solutions are based on actually MOSFET. Okay, I'll just give you one example and you can study about others. So if you look at this particular solution, it is based on a P-channel MOSFET. Now, as you can see, as you know, P-channel MOSFET, it will turn on when drain is at higher potential than the gate. Okay. So now here you can see, if you connect battery in correct polarity, this drain will be having at higher potential than the gate. So the MOSFET will turn on, right? But if you connect battery in the reverse polarity, gate will be at higher potential than the drain. So the MOSFET will remain turned on. So if you connect battery in the reverse polarity, your inverter is not going to work. As simple as that. Because through the diode, negative current won't be allowed. Now for practical application, you cannot simply connect battery directly in parallel to your drain and source terminal. Practically, MOSFET's drain and source terminal maximum voltage withstanding capability could be around 15 to 30 volt. But for a practical four-wheeler, your battery voltage could be as high as 300, 400 volt also. So simply you cannot connect a battery directly in parallel to the MOSFET drain and source or gate and source terminal. So some practical solution I'll be highlighting here. I'll be giving you the part number. In your free time, please go through them. There are 2, 3 other very important concepts here, but due to shortage of time, I'm not going into it. Which talks about whether you should use a P-channel MOSFET or N-channel MOSFET. What are the plus and minus? How do you design such systems? Those itself can be a 1-hour lecture. So I'm just here, I'm sharing you some part number of some practical ICs which you can use, right, for practical reverse polarity protection. The next few protection I'll quickly go through and we'll try to finish the discussion maybe in next 15-20 minutes. This will skip. If time permits, I'll come back. Now, another very important protection is inrush current protection. Right? So, those who are familiar with electrical engineering, you know, inrush current is a kind is unwanted in most of the applications. Now, for our case, this motor control unit, let us have a quick look. What do we mean by inrush current here? Now, practically, when you will be connecting the motor controller unit for the first time with the battery, your capacitor is going to be totally uncharged. The voltage across capacitor is going to be zero. This voltage of battery can be as high as 300, 400 volt. So suddenly, if you connect a battery of 300 volt, let's say, to a uncharged capacitor, you can understand how much current will flow to the capacitor to quickly charge it to the 300 volt, right? Because two voltage source element, they finally must have same voltage because they are connected in parallel here. So capacitor has to charge quickly from 0 volt to around 300 volt in almost no time. To do that, the current it has to sink is very, very high, kind of an impulse response. So that current we are referring here is inrush current, and that can be really damaging for your capacitor, right? So in your converter, you must have protection for against this inrush current. One of the solution is you can use this resistor diode solution I have shown in the earlier slides, like this one, right? So initially, the inrush current or the current used for charging the capacitor will be flown through the diode and this current limiting resistor. So your inrush current problem will be solved. Current will get limited because you're putting a resistor in series. And when the capacitor is charged, then you don't need this diode and resistor. You bypass them through a switch, right? So in steady state, there is not going to be any loss, but at the same time, you have protected your converter from inrush current. And this solution is also can be applicable to prevent reverse polarity protection also, right? Another solution you will see in some low cost product, they use temperature dependent resistor, right? This negative temperature coefficient resistor or positive temperature coefficient resistor, these are some resistor or some combination you can use, right? So for example, let's say if you put a resistor here which will be having higher value at room temperature, right? So then when you connect battery for the first time, there will be some current flowing through the capacitor, but value will be less because resistance value will be high at room temperature. Now as some current is flowing through the resistor, its temperature will increase and at the same time resistance will drop, right? Like this graph you can see for the NTC, this one. So as temperature builds up, your resistance is dropping. Now, if you can select a NTC such that at a slightly higher temperature, let's say 40, 45 degree, it is giving you very low resistance, right? But at room temperature, it is giving you high resistance. So that's how you can solve this inrush current. At the same time, your loss will be limited when you're operating at steady state. This I'll skip. Then you have to protect your converter from over voltage, right? So one example I showed you, LDITT problem may come. Sometime the DC bus voltage may go beyond your rated voltage. So then you have to protect your system, right? So one of the very simple solution is use a voltage divider, measure the voltage which you want to protect, right? So as soon as you see that voltage is getting more than your permissible value, you compare it with the reference value, and then if it goes beyond your required value, you generate a fault signal, and then disconnect the sensitive part from the high voltage or over voltage part. So simply make a sensing arrangement, sense the voltage, compare with the preset value. As soon as you see it is going beyond permissible limit, you trip some part of your circuit so that this part of the circuit is protected from over voltage. Yes. Any questions? Okay, I think someone has turned off the mic by mistake. Similarly, you have to provide protection from overcurrent, right? Over voltage. There is a concept called crowbar protection. Please note it down, and maybe you can learn more about it. Very interesting concept. Another very interesting concept I'm sharing with you, which generally we don't discuss in the class, is adjustable Zener. Now, all of us know Zener diode can be used for voltage regulation, right? And sometimes to protect your circuit from over voltage. But problem with regular Zener diode is that they come with some discrete voltage levels. You may not get a Zener diode at almost every required value, right? They will be available in standard packages, standard voltage levels. Similar to resistance, you know, they are available at some predefined values. They are not available for each and every value. Now, if you're in your design, if you need a Zener diode, which is a non-standard value, then you will be in a problem, right? Because there is no standard Zener diode available for that particular voltage level. So there comes this adjustable Zener. This part number you note down, LM431, very interesting concept. It is an adjustable Zener. Now, by selecting this resistance R1 and R2, as you can see in the screen, you will be able to set your Zener voltage, right? Isn't it amazing? So whatever value you need, you will be able to get it, right? Just by playing with this resistance R1 and R2. And how do you select R1 and R2? Just go through the data sheet of this LM431 and you can use it in your circuit. So whatever value you need, you make a custom solution. These are some practical solutions. I'm not going into detail due to shortage of time. And similar to your overcurrent protection. Now, in practical circuits, the current sensing, either you can use LEM based current sensors, but they are slightly costly, maybe something like this one on the top side of your screen. We generally use in our prototype designs. So basically, they are kind of a IC or shape, or this shape is not clear to you most probably. So basically, this sensor is having a hole at the mid section, and you pass wire of which you want to measure the current, right? So this is an example of current sensor, but these current sensors are slightly expensive. If you want to design your product considering low cost solution, sometimes use resistance, very low value resistance, and connect it in series to the part in which I want to measure the current. So these resistances are known as shunt resistance, right? Kind of bigger resistance with having lesser resistance value. So those current when flowing through those resistance, they will have a voltage drop, and then you compare that voltage drop with respect to a preset value, and you can compare your current whether it is exceeding your desired required value or not, and then you can create a fault signal by passing it through a comparator. And this current sensor also, whether you want to use 3 separate current sensor or only a single current sensor, based on that, there are various configuration possible. Just if you look at these diagrams at piece of your mind in your free time, you will understand how these are being implemented. Then another very important protection is shoot-through protection. Right, those who are familiar with VSI voltage source inverter, you must be knowing this shoot-through protection, or it is available in standard textbook also. So I'm not going into the detail, but this is a absolutely mandatory protection in motor controller unit. Shoot-through protection is absolutely mandatory and necessary. Another very interesting protection is, I'll skip this part, is transient protection, right? And note down this diode, which is a very important, especially for someone who has just started hardware development. Your PCB design skill is not going to be up to the mark. You may have several traces of unwanted inductance in your PCB, right? And then that can lead to those LDIDT, large voltage spikes. To safeguard your sensitive equipment, we always suggest that at least for the beginner level designer, you use transient voltage suppression diodes in your circuits. Okay, these are a special kind of diodes which can suppress those unwanted spikes, right? So I have suggested some part number, and go by this name, search in the Google, and try to understand how they work, how they're different than the Zener diode, how you can use them in your circuit. Otherwise, you will see that at the beginning level to get some result from your power electronic laboratory prototype, it will take months of time. And sometimes you won't be able to understand where exactly that problem is coming. Very difficult to detect for the beginners. So if you put some protection here and there, for example, this transient suppressor diode, your hardware development will be much faster, right? And these are not very costly diode also. No. So you'll be able to manage in your circuit. Another very important protection for practical products are temperature protection. Now, in your whether you are using IGBT, MOSFET, or any other power electronic switches, there will be some losses, right? Conduction loss, switching loss, etc. And your device is going to get heated up. Now, generally, you will be using a heat sink to extract that heat out, and you want to pass it to the ambient. Now, if there is some faulty condition or you are operating beyond your prescribed limit, the amount of heat generation may be higher than for which you have designed your converter, right? So in our practical design, what we do, we put a small temperature sensor near to the important elements, maybe near to the MOSFET, and we get this value. So this temperature sensor, basically they will sense the temperature, and finally at the output they will give you equivalent voltage value. Now that voltage you send it to your microcontroller or TSP, and you know that whether it is getting heated up beyond your prescribed limit or not. So if you see that temperature is going beyond your allowable limit, you restrict your operation. You shut down your system, or you reduce your duty cycle, you reduce your load so that temperature goes down, right? This is very important for practical product design. So I have suggested some part number for you. Please look into them in your free time, right? This part I'll skip. We don't have much time now. Yeah, I think I went a bit fast at this section, but to give you a 1 minute break, can you please help me by naming at least 4 protection that we have discussed for motor controller unit? We have
Yes,
discussed
sir.
more than that. Yes, can you help me?
Reverse polarity protection,
Yes.
over voltage protection, and over current protection, and over temperature protection,
Great.
and shoot through
Okay.
protection.
Sure, protection. Okay. Is there anyone else who can add 1 or 2 other protections, just to see whether you are listening or not? Thank you for your response. Is there anyone else who can tell me any other different 1 or 2 protections? Anyone else? Okay. Maybe you are hesitant, or you agree with all the answers. So I just quickly tell you again. One of the key protection we discussed was those protection from inductor, those LDIDT protection, and we need to use capacitor very close to the switching device locations, right? Physically, that is one of the important protection. We discussed inrush current protection, okay, and several other protections was already mentioned by one of you. Thank you. And now this is again another protection which is very important, especially when you design a product which is for outdoor application. Okay. For example, you will listen from several people that electric vehicles run on battery. What will happen if the battery are in touch with water? So let's say your electric vehicle is running through a waterlogged area, whether it will get damaged or not, right? So this kind of questions, right? And sometimes your motor is exposed to the outside environment, so it will have a lot of dust coming into its body, right? So that it will still able to operate in those harsh condition. So this definition that your product is capable to work at under what environment, this is ingress protection, right? Very important. For example, this is given by this number IP, ingress protection. And if you take an example of IP65, what is saying? The first number 6 defines how your product is protected from the solids, right? So by 6, you are saying that even if your product is operated in a dusty environment, no problem, it can sustain, right? Then number 5, the next number denotes how it is protected from water. So if you just read the number 5, it says have to protect against flashing liquids on the device from any direction. So maybe there may be water splash, right? Maybe during rainy season, or maybe some spillage of water, etc. So from those occasional things, your device must be protected. The motor that we have designed for electric two-wheeler, this is IP67 protected. What does it mean? So it means it is protected from the dusty environment. At the same time, it is protected from water. And you look at this. It says if I have my motor deep into the water for 30 minutes, typically the height will be 1 meter. Okay, so you take the motor and then you submerge in 1 meter of height below the water level and keep it for 30 minutes. Take it out, it should still be able to operate. So that is IP67 protection. So sometimes your electric vehicle may be in a place of waterlogged area. So our motor, if you put it below 1 meter of water for 30 minutes, at least 30 minutes, it is it's not a problem, right? So that gives you better protection from harsh environment. This next topic we'll just touch upon, then we'll wind up this lecture. And in case you have any question, we'll be happy to take, right? So let us imagine that you are driving an electric vehicle late at night and you are visiting a terrorist prone area, which is definitely not a safe area to drive, especially during the night time. And suddenly some part of your vehicle, let's say a inverter we are talking about, let's say one of the MOSFET got damaged. It can be open circuit, it can be short circuit, right? And your vehicle is stopped. And now you can imagine your situation, especially if you are with your family members, you will feel unsafe, right? Your vehicle is completely stopped, you are in a terrorist prone area, and your safety is compromised. So till the time you call a mechanic to come and repair your vehicle, it may be too late, right? Now, another option could have been, even though there is some fault that has occurred in your system, your vehicle is still able to drive, maybe with a lesser speed, lesser torque, but still it will be able to drive, so that you can safely go to a nearby location and you can repair your vehicle, right? So that kind of concept is basically fault tolerant drive, that even if some fault has occurred, no problem, you will be still able to run, right? And it has wide application to several sectors which needs high reliability, like this military, aerospace, automotive industries. And this section, this particular designs are still evolving. It is not yet fully saturated. So those who are looking for a research topic, maybe you can deeply search into this area, and if you're interested, you can also pursue your research in this particular area. So you have to be familiar with several concepts like prognosis. Prognosis is again a very interesting area of research. It basically keeps on measuring some parameter from your existing drive, and it will forecast whether there is a chance that some part of your drive is going to get failure, right? So by drive, I am referring here motor plus motor controller, both of them together. So maybe you can forecast that your motor is going to get damaged in, let's say, 5 days, 6 days, like that. So that well ahead in time, you can repair it. So that is prognosis. So you keep on monitoring, let's say, temperature of the winding, resistance of the winding, and some other parameters, right? And you can take a call. So now if you can tell in advance that your solution is going to give you some trouble, it's going to be faulty, definitely you can take action while ahead in time and you can be safe, right? Another term is diagnostic. So basically some fault has occurred. Now how do you determine what exactly has happened? So that is basically diagnostic. By tolerant we mean that capability to endure specific conditions or treatment. So some fault has happened, but still you are tolerant. You can still drive, right? And fail safe is basically you are designing in such a condition that it will never break down. Now, whenever you are discussing this motor drive for electric vehicle, you have several components. One is your power supply, basically the battery unit, and you have the inverter, basically the VSI unit. You have a controller for the inverter where you'll be writing all your codes. Then you'll have a lot of sensors which will be sending information to the controller, and of course you'll be having the motor itself. And then in several places you need a DC-DC converter most of the time to give power supply to your several ICs. Your microcontroller needs power supply, driver circuit needs power supply, sensing arrangement they need power supply. So those power supplies are generally derived from your input battery itself. Now, in these different segments, there are several chances of getting faults. So I'll just I've listed few of them for your reference. You go through them in your free time. So in the battery, there may be several faults. Some of them we already discussed. Then in the stator of your motor, there may be several faults: inductance short, phase winding short, open, etc. In the rotor, there may be several faults, especially in the from the permanent magnet side or in the alignment side, right? So these faults have several categories. Again, we are not going to into details, but if you study those faults, there are different categories, right? Now, how your system is tolerant to this kind of fault, that that study itself, as I said earlier, it is not yet saturated. You may spend some time, and definitely you'll get some research problem out of it if you're interested. So here I'm highlighting few faults, like one particular switch, if it is get open circuited, what will happen, how you can prevent it from completely stopping your vehicle, those sort of some solution which is provided in literature. I have highlighted here. Reference I have already mentioned, so that if you are interested, you can go into deep in this particular areas. Due to shortage of time, I am not explaining you the exact circuit operations, but I am showing you some interesting circuit topologies, and I'm sure if you get time, you would love to study them. This will give you some different ideas, right? For example, this particular inverter, if you see, generally in our solutions, we keep this neutral terminal floating, right? In our practical most of the solutions, but here they have connected battery between negative bus and that neutral terminal of the motor, whereas at the input side of the inverter they've just connected a capacitor. There is no battery, and through some analysis they've shown that this solution is equivalent to a battery followed by a DC-DC boost converter, then followed by a traditional inverter. So without using switch count, you are actually giving two solutions simultaneously, two converters simultaneously, and at the same time, you can design, you can control the scheme such that you can have some fault tolerant operation. But still, this scheme has a few problems. Maybe you would like to see, and you can improve this further, right? So these are some interesting work, and there are several other work which are not yet very saturated, still have a lot of challenges. Mostly this fault operations, and another very important term, right? Functional safety. This research area is again a very interesting, especially in Indian context. Functional safety, uh, and it has several areas to work on, especially for our electric three-wheeler, two-wheeler, those areas. See, in most of the developing countries, they have done a lot of work already on the four-wheeler front. But this three-wheeler, which is very popular in developing countries or underdeveloped countries, a lot of work are still remaining with them, especially on the safety front. So if you're interested, spend some time with them. I'm sure you'll get some interesting problem statements. And if you can make them fault tolerant, more safe, not only you will get a research publication, at the same time you are contributing to the society also. And in that front, I would like to highlight that in India, there are several startup companies who are doing very good job, right? For example, Ether Energy, then Liger Mobility, etc. So if you are interested, come up with some idea. There are a lot of supports from different institutions, different industries to incubate startups, right? If you are a faculty, please encourage your students to uh, come up with some novel ideas, do something on their own and contribute to the society. With this, I thank you for attending my long this discussion session, especially organizing team for giving me the opportunity. I'll be happy to address your questions if you have any. And if still you want to connect to me offline, please write an email to me using this email ID provided in this slide. Also, I have a YouTube channel where I have uploaded some demonstration videos, especially for our laboratories. If you love to see more of them, you may suggest me a particular topic, and I'll see if I can do that. I also request you to connect me through LinkedIn. The link is given here, and there we can discuss this different collaboration possibilities, research problem, etc. With this, I wind up. Thank you for being such a nice audience. If you have any question, please feel free to.
Participants can ask the questions to the
Of course, if you don't have any question, you can go for a quick lunch.
I think there are no more questions, I think, sir. Thank you, sir, for delivering such a wonderful lecture. I hope I have one question in the chat box, sir.
Okay. Yeah. Can you please?
Yes.
No. Okay.
Sir, about fault tolerant microgrid, where to study? Sorry, am I audible, sir? The question was, he was asking about fault tolerant microgrid.
Yes.
Where can he able to study?
Yes. I'm not studying much about the microgrid and its fault tolerant structure. Maybe I'll look into it, and can you please drop me an email? I'll search and I'll get back to you. Definitely, you can try on the IEEE website. You should get few, but I can also help you. Just drop me an email. At this point, I don't have clear answer to this question. Sorry.
Any other questions from participants? I hope. Okay, sir. I think there are no more questions from our participants side. Thank you, sir, for delivering such a wonderful lecture. I hope our participants utilize to their maximum benefits. Thank you very much.
Thank you, sir. It was very nice presentation. So thank you, sir.